solution to chapter 7 and 8 shortly. The objective of this function, this chapter, is to understand the physical mechanism of natural convection. For forced convection, we know there is air is fluid moving, there is a certain velocity, therefore we have the velocity, and from the velocity we were able to calculate the Reynolds number, and from that, is it natural, is it laminar or turbulent, and we were trying to find that one. Derive the equivalent equation for natural convection and obtain the dimensionless. Now we find a new dimensionless that's related to natural convection. In forced convection, you calculate a Reynolds number. In natural convection, we calculate a Grashof number. Again, it's the dimensionless number. Okay. The question here: what is exactly natural Grashof number represent? Okay, that's we have to understand. Because in Reynolds number, we're looking at the ratio of force to friction, right? Yeah, this is, again, we have to find out exactly. Again, we're trying to look at different case, evaluate the Nusselt number. Again, we calculate based on Grashof number, we calculate Nusselt number for associated with a vertical wall, horizontal, or it could be the case of wall, it could be related to a ceiling or floor, that's horizontal means. Inclined plate, like attached, like we have here, attics and roof. And for the case of cylinder and a sphere. Therefore, we're trying to find is appropriate set of equation of correlation for a case of when we have vertical wall, we have a horizontal. Again, horizontal, it means it could be ceiling or it could be floor. And it could be inclined like attics, like here, okay? And also other geometry. And then we try to find the natural convection inside enclosure, because sometimes we have a glass, two glass of the window. There's no fan, but there is a natural convection in between, because we call it, in this case, we call it enclosure. Okay? Enclosure, it means that case that we're dealing. And then we sometimes look at here is, so we have wind, but also we have natural convection. When I can make a decision which one is dominating, okay? Therefore, in some cases, both of them can play a crucial role. Therefore, forced convection can be as important as natural convection. Therefore, that case, we have to calculate the combined case. In here, probably there is no forced convection, there is no fan, there is no wind, only the temperature difference. In some case, we have a temperature difference, but also there is external flow like fan, okay? This is, we're trying to learn through this chapter, okay? Therefore, we look at mechanism. We are trying to look at how we define this number, how we can obtain it, how we can indicate this is a crucial factor. And then we're trying to develop sort of a set of equation or use a set of equation to look at Nusselt number. And then we look at the same case that we have for case for enclosure. And then we look at what scenario, which indicator, again, here is an indicator will reflect which one is important, okay? And the easiest one that the egg always we mention here, this is that you have seen, you have taken it, and this is hot, you bring it in the morning and you put in the plate, and after a while it gets cooled down. The reason here is the air comes here, approach to the egg is hot because it was boiling in the water, and then there are some heat transfer between the air close to the egg. The air gets warmer, as become warmer, the density will drop and slowly move up, okay? Therefore, this can move up just because of the, we call it the buoyancy force, because the air gets lighter and will go up there, okay? As it gets up here, there is some pressure that comes in. Therefore, this is will take place. Therefore, here we're looking example again. This is we have using all the time. If you look at your computer that you have, is there are a lot of heat generation inside, and those heat generation are dissipated by natural convection. There is no fan inside. All of them is done by your TV. Okay, all of this these days are cooled down by natural convection. Okay, so if you look at old computers are big because there was a fan in the back, it was blowing. But now they're trying to make this one. The same thing that you can see it. You have we discuss about the cold here. The air comes here, exchanged to here by natural convection, and get colder. In this case, the pattern here is here. Before, the pattern was up. In this case, the pattern is down. Warm will come here, get colder. As get colder, become denser. As become denser, will go down. As it goes down, some fresh air comes here. Therefore, this happens all the time. Therefore, read the motion that's result from continual replacement of the hot air, the heated air, close to the warm here, goes down here and get the, this is happening. Therefore, now there is no external forces. All this air movement, I call air movement, that's the terminology you have to look at here. The terminology here is this air movement take place because of temperature difference. Temperature difference causes this this phenomena take place. Any question? If you look at, this is the way me or you, we are dissipating heat from our body. Inside our body, heat is generated around 65, 70 watt. All of them will dissipate into environment, and that's by natural convection, okay? Therefore, my skin is around 37 degrees sort of. That air is 20, therefore that's heat is generated in living environment, okay? If you look at here, this is the case that you have here. The same way we had a laminar and turbulent flow. For the forced convection, the same thing that we had for natural convection. This represents a natural convection. Look at here, all the streamlines are parallel, okay? There's no intersection between them. Therefore, here is denser because there is more temperature gradient, and we go here, slowly temperature, right? If you look at the turbulent, you can see here, there is a mixed in here, and that will happen. In natural convection, no blower are used. Therefore, the flow cannot be controlled externally. Therefore, there is no way that you control the finance one. There's no control. It happened automatically by itself. The flow rate in this case is established by dynamic balance of buoyant force and friction force. What that means here is the buoyant force is the air become lighter. For example, in the case of heating, it's going up, but it's closer to the wall. And as you know, the velocity on the wall is zero because of the viscosity. Therefore, air will go up, but viscosity keeping. Therefore, this is the two forces are balancing each other. The smooth and parallel line, in case of this one, indicate the flow is laminar. Look at here, it's not. And irregularity, turbulence is represent turbulence. Therefore, that's again we have, in case of natural flow, natural convection, we have also again, we have the terminology laminar flow and turbulent flow. We have to understand these two cases together. As you can mention before, this line, you can see it, there's closest together, indicate a higher temperature gradient. Okay, here the temperature gradient here. As move out, temperature difference become less. That's why we have it. Any question, please? Any question? Do you have any understanding what is natural convection and what is the mechanism behind it? Natural convection, the case that there is no external forces, the air move, there's some air movement, and that air movement because of the temperature difference. And there are two forces acting on the system. One is buoyancy forces, and that's happened because of the density difference between the air right here and the air here. Therefore, there's a temperature difference, and therefore there is a density difference. The air closest to the wall, if it's the heated wall here, this is the heated wall, you can see the temperature is higher, therefore the density is different here. Therefore, this one move up, and from here, colder air comes here. And again, look at here, at the beginning here, assume this is non-slip condition that we have. The air velocity is zero, and that's slowly moving. Okay?
Sir?
Yes, sir.
For when I was doing the project, I was wondering because I put my convective heat transfer inside, and I took that value from the book of from building science that we had, and I said I took that value from building something, and it says cold climate. And as a comment, the marker said, "Do you consider your house to be within a cold climate?" So I was wondering, is um, the convective heat transfer inside a house, which we can consider the velocity of the air being around the same if we're in a cold or a hot climate, isn't it? So
The temperature should be the same because both of them are we design our houses in Nunavut up there or down in California. We're trying to have it in the sort of comfort zone. And
so
if there is no mechanically ventilated building, therefore we assume that's the case. And then we also assume that both follow the building code and the temperature on the inside the wall are almost the same, okay? Therefore, I believe his comment, again, I believe needs that you justify why you mentioned cold climate. Even though Africa, Northern Africa, northern part of Africa, I believe it's mentioned that was northern part of Africa, it's not a cold zone area.
Yeah, but it was in the name of the book. But what I'm asking is, does the heat transfer coefficient would change if it's a hot or a cold climate, or it only depends on temperature? So that's what I thought. The air velocity inside
only depend on the temperature difference.
That's it.
Temperature difference. What is the temperature of the wall, interior surface of the wall, and room air? And if you follow the building code. Therefore, we design the wall in the way the temperature inside the wall here will not be minus 20 degrees. Get closer to.
Okay, thank you.
No problem. Therefore, if you look at here, this is exactly happening. Here is assume this is the wall, vertical plate, and we assume the temperature here is TS, is temperature of the surface, uniform temperature, and here we assume is the temperature of the air. Okay. Therefore, in this case, the TS is higher than the T infinity, the room air. And if you measure the temperature from the wall surface, moving out slowly, we can see the temperature drop. And after a certain point, the temperature here is remain the temperature. Therefore, everywhere here is the temperature infinity. Therefore, this represents your temperature profile of the air. This is the temperature profile of the air. Therefore, as you can see, at this point, you have a bigger temperature difference than here. Here, the temperature is Ts minus T infinity. Here is T infinity minus T infinity. There's no temperature difference. Therefore, here, this represents your boundary layer. Therefore, this is your temperature profile. And also, we are considering non-slip condition. The velocity here is 0. Therefore, on the surface of the wall, the velocity is 0. And because of the viscosity, the velocity profile will increase slowly to a certain point and then drop here. Why drop? Because as we go further, the temperature difference becomes 0. Therefore, there is less buoyancy phenomenon. Therefore, this represents your velocity profile and this represents the temperature profile. This is in the case of that we have heating process. Therefore, the temperature of the plate or the wall is more than the temperature of the fluid, okay? If it's the reverse, this window in the winter, this temperature is cold. Therefore, this temperature profile becomes inverse and this velocity becomes inverse. Therefore, the first thing here is we have to really understand what is happening. It's happening here is we have a temperature difference. As a result, we have a buoyancy density difference. Therefore, here the temperature Ts, here is the infinity. Therefore, the air here is hotter. It will go up. And here, the temperature difference between this point and this point is the same. Therefore, the velocity is 0. Okay. And velocity profile becomes like this for the simple reason because of the viscosity phenomenon. In the surface of the wall, the temperature, the velocity is 0 because of the viscosity. And at this point, the velocity is 0 because there is no temperature difference. Therefore, this ends up become your velocity profile. Any question? Okay. Therefore, if you look at here, unlike forced convection, the fluid velocity is 0 at the outlet. It means the velocity here is 0. In the forced convection, the velocity it was the highest because there was no viscosity phenomenon. But here is 0 because the temperature difference between this point and air, therefore there's no density difference. Unlike forced convection, the velocity, fluid velocity is 0 at the outer edge of the velocity boundary layer. Okay, at this point, the velocity is 0. As well as wall surface. Here, because of viscosity phenomena, here's because there is no temperature difference between the air at this layer, at this layer. The temperature difference is 0. Okay? At the surface, the fluid temperature is equal to the plate temperature. Here is Ts, or here is Ts, and gradually decrease to the temperature of the sounding air. Therefore, as we get further from the plate, the temperature drop. After a certain distance, the temperature remain constant. The temperature of the air is the same, okay? Try to really understand and try to visualize the physical phenomena, okay? In case of the cold surface, if this is the Ts is less than T infinity, this become opposite, up down. The velocity profile become like this, and the temperature profile become like this, okay? Therefore, that's the difference between them. As I mentioned now, here there are two processes taking place. The first one is buoyancy phenomena. Buoyancy phenomena, it means we have two columns of the air, one column here and one column here. This column is T infinity is less than here. It's cold. Here is temperature change from here to here. Therefore, the density here is lighter. It will go up, and this will come down here. And the same time, because of the non-slip condition, the viscosity on the surface is equal viscosity. Therefore, we have velocity 0. The velocity here is 0 because of the viscosity. As we get further here, the temperature difference is less. Therefore, the density difference is less. Therefore, the velocity becomes 0. Okay, let me move. If you have any question, please do ask. We go back and try to really find, now we understand visually what's happening. Now let's relate to also the equation, because we mentioned there's something called Grashof number. I'm trying to find out where this Grashof number comes from. Okay, this is the density difference I mentioned here. Is the density as temperature infinity. This is temperature surface. Okay, therefore this is phenomenal. Okay, let's go here. We take a control volume as we did it for forced convection. The same, we try to find the continuity equation, the momentum equation, and energy equation. We try to write these three equations because these are the base equation that we look at it. If you remember, these are the force acting on the system. This is the control volume. This is I take a control volume here. I take a control volume here. Here the control volume. I'm trying to write force balance on that one. Therefore, this is down, shear, this is going up. And this is the pressure difference causing the system go up or down, depending if it's heating or cooling. Therefore, this becomes my force balance equation that we did it in chapter 7, 6, 7, 8. And if we simplify this equation, I will end up with this equation. This part, this is related to my momentum I have. This is my shear force, and this is the temperature difference. This is the pressure difference here, and also the last term because of the density, the pressure that coming to the system. And if we simplify here, this represents rho g. It means P infinity minus this one. Okay. If we put all of them in the same equation, this becomes this part, become this term. This is my shear force, and this is the buoyancy force I was referring. The two columns of air that I have. One is related to bulk temperature, and the other one related to the boundary condition, that the density in the boundary layer. Okay. Now therefore this is similar to the same equation that before we did in chapter 7 and 8. We ignored this part because it was forced convection and it was sort of constant, this term. And if you put them in together, I can always refer to this density as a function of using ideal gas law. I put in the form of the temperature, and therefore this temperature represents my momentum equation. These are that I have, these are related to the momentum that we discussed in the previous chapter. This is my viscosity phenomenon right here. And this is because of the temperature difference between the bulk and so on. Okay, this is my equation. Okay, depending on the scenario, we can try to solve this equation to find the temperature profile and so on. But let's go one step further. Therefore, this one we had a continuous equation, the same as before. This one we momentum equation that now we have an extra term here. And if I write also an energy balance equation, the same as before, I end up with, this is my convection term and this is my conduction term. Therefore, we have to solve this three set of equation, find velocity, the relation between these two, replace it here, find a function for u and put it in here and find the equation for the temperature. And these are my boundary condition. These are my boundary equation that I have. At x equals 0 and y, temperature along the plate is Ts, okay? Outside is T infinity, and the same thing for velocity profile. The effort is not to solve this differential equation at this moment. The effort we're trying to find the contributing sort of the important parameter. To do that, we always go and non-dimensionalize this equation again. A non-dimensional equation, again, we do this one. We use a length, characteristic length to non-dimensional velocity, undisturbed velocity, and also the temperature. When I non-dimensionalize equation, I end up a term here, this term right here, this term here. I have the Reynolds number that I had it before, and I have Reynolds number I had before. Therefore, now we see these are non-dimensionalized. Therefore, we can see the behavior of this is a function of this 9-dimensional term that I have here. If I look at carefully, this is representing something, okay? You have to find out what exactly it's representing. Therefore, this is called Grashof number. The Grashof number that we have is a G, 9.8, beta is 1 over T, temperature of the surface, temperature of the liquid. This is a characteristic length. Again, please, my friend, remember characteristic length, and this is kinematic viscosity, okay? Therefore, this is called Grashof numbers. And that's represent the nature of my natural convection. And this
What's the beta again, please?
Pardon me?
What's the beta?
Beta is expansion coefficient, is 1 over T.
Okay, thanks.
Okay. Yeah. Okay, therefore here is, we can mention right here, G, beta is convection, it's 1 over the temperature. This is 1 over the temperature, represent the expansion coefficient for ideal gas. And here is Ts, T infinity, so okay. Therefore now we look at here, we can see now, when we normalize the equation, these are normalized equation, therefore we can see there's one factor here, the one factor, and if you put all this dimension here, this becomes dimensionless, okay? Reynolds number is dimensionless here, and look at here. We have one function over Reynolds number square, okay? Remember here, this one, this is very important to keep in mind, okay? Because this represents natural convection, this represents forced convection. Again, we have to come back and revisit this one later on. But let's focus on Grashof number. Therefore, Grashof number is, again, a dimensionless number that is specified if the natural convection is laminar or turbulent. Again, what is exactly natural convection? This, again, we go back to what we discussed earlier. This is a hot plate. The air gets warmer. As it gets warmer, it becomes less dense and it's moving up. But this is close to the wall and there's a friction, there is a viscosity here, it's pushing down. Now, Grashof number represents the ratio of these two forces. Buoyancy forces, temperature difference right here, buoyancy forces, to viscosity forces. Therefore, that again, Grashof number is representing a physical phenomenon. The ratio of buoyancy force to friction force. If this one is stronger, the fluid moves up. If it's not, there's no motion, okay? When a surface is subject to external flow, the problem involves both natural and forced convection. And that's going back here. You have natural convection and you have forced convection. This representing, and now we have to decide when this one is dominating, when this one is dominating, or when both of them are dominating. When a surface is subjected to external flow, it means you have a fan or something. The problem involves both natural and forced convection. And this ratio, again, this ratio that represents this one, Grashof number is over Reynolds number squared. This one is representing both of them. Natural convection can be negligible, natural convection, if this one is less. That means this Reynolds number is so big that we can ignore this one. If it's bigger than this one, we can consider it's free convection. If it's almost equal, we can assume both of them are contributing. Natural convection is contributing and forced convection. Again, you will see it later in your textbook. This number was, again, by itself called Gratz number. Grashof number over Reynolds number called Gratz number. You will see it in textbook. Okay? Therefore, now we have a Reynolds number if it's forced convection. We have Grashof number if it's natural convection. And if there is a case that we have to look at both, again, here is Grashof number is about this one. For vertical, the critical Grashof number, if it's less than 10 to the power 9, is laminar. If it's more than that, is forced convection, okay? Therefore, now we'll come back and revisit this one. If you would like to try, yes, sir.
Can you go back to the previous slide? Just one slide? Yes, 1 second.
Sure. I'm sorry, let me know because I cannot see your face. I have no idea. Please, if I go fast, let me know because I have to use my imagination.
All good, thank you.
Okay. Therefore, now we have this ratio. If you would like to visualize what exactly that means, is like this. Look at here. In this case, we have natural flow. There's no forced convection. Therefore, in this case, this is bigger than 1 because Reynolds number is none there. Okay. In this case, if you look at here, Grashof number, you can see the flow is into visualization. Look at here. The natural convection does not do anything. You just follow the forced convection. Therefore, here is forced convection is dominating. But look at here, it's going this direction. It means natural convection contribute and forced convection is a contribute. Therefore, if you would like to visualize it, that's the sense that you have here. In this case, the fan has no function. You can put a fan here, just visualize it, but the velocity is so small that flow is going this direction. It means it's dominated by natural flow, by temperature difference. If you look at here, the streamline is in parallel with the forced convection. It means natural convection has nothing to do with it. But if you look at here, is influenced by the forced convection and also by natural convection going this direction, okay? Therefore, in some cases, we can only ignore forced convection. Some cases do this one. Therefore, we have to calculate always this number here and to see if it's fall in this range, or in this range. Okay? Any question, please? Okay. Ask me, please. Now, if you look at here, the same thing that we had it for forced convection, we mentioned in general term, we write the Nusselt number as a function of Grashof number. That's similar to the Reynolds number that we have, Prandtl number to power n. Therefore, this represents all the general term equation, okay? But also, we have Grashof number times Prandtl number called Rayleigh number. Therefore, Rayleigh number is simply the Grashof number times Grashof number is, just a second, please. Okay, sorry. Therefore, we can mention general form. The general format. Nusselt number can be always defined in this format. Grashof number times Prandtl number to power n and time coefficient. Therefore, and sometimes they define this multiplication of Grashof number and Prandtl number as Rayleigh number. This is RA, is not RE. Therefore, this is called Rayleigh number, okay? Therefore, we can define Rayleigh number. This is the Grashof number right now you have here times Prandtl number, okay? Therefore, when you hear Grashof number and Rayleigh number is almost the same for a given gas because this is only a physical property of the material. Therefore, let's look at here. Now, natural convection heat transfer on the surface depend on the geometry. If it's plane, plate, if it's cylindrical, or is it spherical, as well as its orientation, if it's vertical or if it's horizontal, and temperature variation on the surface, okay? Therefore, this is cooling or heating, and the thermophysical property of the fluid, okay? Therefore, these are the dominating factor, and all of them has been sort of summarized in this expression. And C here is probably represented, so the coefficient, depending if it's vertical, horizontal, and N and so on. The constants C and N are dependent on the geometry and of the surface and the flow regime, which characterized by the range of Rayleigh number. The value of N right here, usually is not all the time, usually is 1/4 for laminar flow and 1/3 for turbulent flow. As I mentioned, usually they put it because most of the work is done experimentally. We have experimentally data, and we're trying to fit those experimental data on the equation like this, okay? That's the experiment. Again, something you have to keep in mind here is all the physical property. What do I mean here? We have Prandtl number, it's a physical property, kinematic viscosity, all of them are calculated at film temperature. Beta is also a physical characteristic. It's calculated based 1/FF. Therefore, beta here is defined 1 over this temperature, okay? Therefore, in general, we can go back again. We mentioned this is a convective heat transfer between the surface and the air. Therefore, the general equation is that T is the temperature of the surface, T infinity is the room, the bulk temperature in the room, and H here is unknown that we have to calculate. This H is H here and is based on your Rayleigh number, geometry, orientation, and so on. Therefore, first I have to go calculate the Grashof number, identifies laminar, turbulent, and so on, and then look at physical property, then come back here based on appropriate correlation that I have, to calculate my heat transfer coefficient. Okay?
Sir?
Yes, sir.
When it says all fluid properties are to be evaluated at TF, it includes the PR number, right? Prandtl number.
Absolutely.
Okay.
Absolutely, sir. Let me go to next slide. And next slide, if you look at here, now you have a table 9.1. And here give you the geometry that you have. Again, we define characteristic length. Remember, characteristic length, when you're using those equations, characteristic length is very, very important. And then in range of a Rayleigh number, here is RA, Rayleigh number, laminar or turbulent, and so on. Therefore, this, if it's in this range, less than 10.9, this was a critical number, you use this equation. If it's turbulent, use this one. As you may notice, again, here is mentioned, for laminar flow, the power is 1/4, for turbulent is 1/3, okay? Again, this is simplified equation. This is a simplified equation. They make it easy to use. But this equation is give you the same answer, and it's correct from 10 to the power 4 to 10 to the power 11. Okay, that's just, again, as I mentioned, they are trying to fit a curve, fit the equation in a curve. This is, they realize that if they break it down in two range, this is easy. When it become incline, there's like an attic that you have a surface like this, attic right here. Therefore, this is, we can look at it. Therefore, you can calculate base, you mentioned use the vertical and multiply by cosine of theta. Okay. Again, it come back to the real life. This is representing a floor, assuming the bottom part is insulated and the temperature of the floor, that the case that you have here, Ts. Therefore, if you look at here, the air is going up here because the temperature surface high, therefore are going up. Therefore, you're using this equation. And if it's the case in the bottom here, the temperature here is hot surface, you're using this equation. Again, keep in mind, characteristic, what is the length for this one? What is the length for this one that you have here? Because here you can define length. Here you can define length. But here, when it comes a horizontal plate, how can you define the length? Therefore, they define this as define. Surface area divided by perimeter. Therefore, they define a characteristic length that fit in this equation. Therefore, when you're dealing with horizontal plate, your characteristic length is area divided by perimeter, okay? Keep in mind, that's the way it is done. Again, we have to look at case by case. Mention upper surface of the hot plate for lower surface of the cold plate. Lower surface of a hot plate or upper surface. Therefore, you have to find out which scenario that you're dealing, that you're kind of at. Therefore, first read the problem, understand the physical phenomena, and then calculate your Rayleigh number. Rayleigh number is simply Grashof number times Prandtl number. And find in this range, which range it is, then use appropriate correlation. Okay. Again, we have table 0.9.1, it has continuation, and continuation comes for cylindrical coordinate. For example, in most of case that we are doing studying research, we assume human being is a cylinder, okay? Therefore, we can calculate, use this geometry to calculate the value over there, okay? If it's horizontal, if it's like this. If it's spherical, like this. Therefore, mention if it's horizontal, if it's vertical, you can use it, treat it as a vertical plate as long as the diameter is more than this one. Therefore, when you're trying to do this one, you can use the same correlation as this one, but you have to make sure that satisfy this condition, okay? Therefore, now you have a range of sort of expression. I call it correlation. And for that, as I mentioned again before, most of them has been obtained experimentally. And therefore, we have a set of correlation. These are representing a certain range. But if you could look at different textbooks, you can see different equation. Again, all of them was based on trying to fit the curve. And then if you're dealing with really sophisticated design, you have to go back to the library and try to look at the handbook to find out the case. Okay, having said that, let's go back to this problem. Read the problem. Again, the problem, I believe is from your textbook 947, if I'm not making a mistake. I don't know if it's 5th edition or 6th edition. A can of oil. Therefore, now we are dealing with the cylindrical coordinate. It mentioned the dimension. It mentioned the length. And mentioned the temperature of the surface. And therefore, it also mentioned the temperature of the air in the trunk of the car, okay? In the summer day, you put in the back of the car, and because of the heat, the temperature of The trunk is around 43 degrees. Read this problem and I go back to those equations that you can start to play with it. Therefore, the only number that you need at this moment, here is the diameter. The length is 150, the diameter is 100 millimeter, the room temperature is 43 degree, and the temperature of the surface is 17 degree. And cylindrical coordinate, we have to go back here and mention if the case, we can go back and use this one. Now we have to find if it's this in this range or this range, okay? Therefore, anyway, we take the length of the cylinder as characteristic length, and we have to go and calculate the Rayleigh number. Therefore, the Rayleigh number is this one. G beta Ts, that we know the temperature we know that. Characteristic length is the length, the height of the cylinder. And now we have to go and look at some of this value of physical property. All of this physical property calculated at this temperature. Therefore, we know the temperature. Yes, sir.
Can you show the question again? I didn't find the Ts to infinity. I didn't write it down. Okay.
43 and 17. The average become TF become 30. Okay. Therefore, you have to go back, and I do not know which table was for air. Was it 15?
I think it was 15, yeah.
Okay, you go table 15, A15, and look at the T film, TF 30 degrees, and you look at kinematic viscosity. You look at the Prandtl number, and I believe also you have in last column beta 1 over TF. Therefore, 1 over 30.033, right? Therefore, you can calculate, and you can go back and calculate your Grashof number, Rayleigh number, 9.8. This has to be, I made a mistake. This has to be in Kelvin. It means 30 plus 273, okay? Therefore, this is 1 over 30 plus 273, 303, okay? Therefore, your beta is 1 over 1303. You have TS 43, TS, what was it? 17, T infinity, and this number, these two numbers come from the table. You calculate your Rayleigh number, okay? And then you check your Rayleigh number if it's laminar or turbulent. Therefore, you come here to see if it's this range or in this range. If you don't want to bother, you can go straight and use this equation. But this one is much easier to use.
Sir?
Yes, sir.
I don't think there's the beta, the coefficient in the table.
It's
I can't
not
find it.
I cannot in one of the columns, supposed to be the last columm. Let me see.
No, the last column, it's for air, it's PR.
And the number. But again, it's very easy. It's you calculate it is 1 over TF. But T is in Kelvin, okay?
Okay, so 1 over 43 plus 273.
That's right.
Okay, okay, perfect.
Oh, 1 over 30 plus 273. TF.
Yep.
Sir, if you look at the table 8.9, I have it here is for, what is it, is for?
It's not air.
Is water here, let me go 15, right? 12, right? You mentioned 12.
A15.
A15. I haven't had my lunch, therefore my memory is not working properly. Yes, for that one, that was not given. because it's easy to calculate. But for the other one, for A14, for other material is given, but not for, because this is easy to calculate. But for some of the gas and liquid, it's given in the table. Okay, let's go and see where we are. Therefore here, (30°) kinematic viscosity Prandtl number, and this is 1 over TF. Remember, this TF is in Kelvin. It means 273 plus 30°, become 303. Therefore, become 1 over 3 over 3. This become this one. Okay, this is Kelvin. Okay, make sure. And then we go back and we calculate the Grashof number or Rayleigh number. You can see here, this is the value of G, beta value. This is temperature difference. This is the characteristic length. It mentions the can is 15 centimeter. And here, this is the kinematic viscosity. My friend, remember, because I know some of you have this tendency to forget, this is to power 2, this is to power 3. Based on my experience of past 25 years, 30 years, somehow some of you are missing this power in your calculation. Kinematic viscosity to power 2, characteristic length to power 3. And you can see the Prandtl number, the Rayleigh number become this one. This is less than 10 to power 9. Therefore, this is laminar flow. Therefore, if you would like to go back, you can see you can use this equation because it's in this range. In this range, therefore, this is power. This is laminar, you can use this equation, okay? But also, I'm sorry, I also mentioned the only time you can use that one if this condition is satisfied. If this condition is satisfied. We have the characteristic length, we have Grashof number, we can verify this one, okay? Okay. Therefore, this is.
What if it actually is bigger than that value? What do we can only
diameter.
Okay.
This diameter,
if it's under?
If it's bigger than this one, you can go and use this correlation here.
Okay.
If it's not, otherwise, you have to go and look at other textbooks because there are some other equations.
Okay. Okay.
Here they're trying to give you just some basic equation, because if you go to other textbook, you can see that even this equation are different from the other textbook. If you can see this one, if you calculate, this value is less than 15 centimeter. Therefore, this is justified to use the correlation that has been developed for a vertical plate. Now you go
Grashof number?
Grashof number is this one, sir. This is the Grashof number. This is the part.
Okay, thanks.
Okay. Grashof number is G beta and so on. Therefore, this is the calculation. If you calculate this part, you calculate this part, or you just divide this number, but divide this number by Prandtl number, become Grashof number. Because the Rayleigh number is Grashof number times Prandtl number. The Grashof number can be calculated this divided by this, become your Grashof number. Okay, therefore now you have the correlation from table this one. I'm sorry again, from here, and you can go and calculate your Nusselt number. Could you please calculate the Nusselt number and tell me what is the heat transfer coefficient?
Sir, can you show the question?
Yes, sir.
Okay. Thank you.
Excuse me,
Yes, sir.
sir. For the vertical cylinder we talk about, um, could you go back to the formula for 1 second? Yeah, not this one, one before. Yeah, this one. On the right, laminar.
Yes,
Okay, and the second one is for turbulent, right?
that's correct, sir.
Okay, what about the third one?
It mentioned you can use it from 10 to power 4 to 10 minus 13. Therefore, it mentioned for the entire range. This correlation can be used from this number to this number. Therefore,
Okay,
if you use this equation, it's supposed to give you a similar answer to this one. There is some differences just because they have a curve and trying to fit that curve in this equation.
okay, thanks.
Okay, we mentioned here is more complex, but not necessarily more accurate. Okay, therefore, all of them again. The problem with convection is most of the work has been done experimentally. Therefore, sometimes the error can be 10%, 20%, 30%, so on. Okay.
Okay, I see.
It is not based on solving the differential equation. They carry out experiment with different type of gas, with different size, with different temperature difference, and they find different value and they put them in a curve. Okay. Therefore, if you go here, you can see the Nusselt number is 31.38. And then knowing the Nusselt number, you can calculate your heat transfer coefficient. Therefore, this Nusselt number is equal to HLC divided by K. Okay, write it down, please. Please do ask question.
LC is the same as before, 0.15, right?
And C is the characteristic length, is the length, yes.
Okay.
Okay, therefore, let's move to the next slide. And you have the Nusselt number. You can calculate your heat transfer coefficient. And if you look at heat transfer coefficient, is 5.14. Okay, this is your heat transfer coefficient. You go back and replace it in your Newton cooling law, and that's equal to HA, the surface area, and the temperature difference. And this is a cylinder, therefore this is heat transfer from the surface of the wall. PD is the perimeter, and L is the length of the pipe. Okay. Therefore, now you know that the heat transfer is equal to 6.63 watt. Okay.
Sir, when we calculate Nusselt number, we have different formulas to choose. In the table, I saw the formula you introduced is for the vertical plane, right?
Let me finish this slide and I go back and explain. As I mentioned, we have an equation for vertical plate. And if you go look at the table 9.1, if you have your textbook, it mentioned if you have a cylinder, as long as these conditions apply, that D is less than that value, you can assume this is a vertical wall. Therefore, you can treat the cylinder as a vertical plate and use it.
Okay. So the D you talk about is diameter of the cylinder.
That's right. This is the diameter of the can.
Okay.
It is mentioned. Sorry.
Okay, thanks.
Sure. Done. Can I move now? Therefore, now we look at here that in the case, if there is no forced convection and the heat transfer is only due to the temperature difference, we call it natural convection or free convection. If you read different textbooks, they use natural convection, some of the textbooks, the free convection. And now we have a procedure to calculate. And one of the indicators is the Grashof number. Therefore, in the case of natural convection, we go and calculate the Grashof number and trying to find out how important that phenomenon is. Okay, could be laminar, it could be turbulent. Now we have a table, they give us few samples. These are a sample of correlation for some geometry, okay? Now, again, it's can happen, it could be again for inclined surface, okay? We will have, again, this is the for vertical plate. If forced convection, it means if we have constant heat flux. If you have vertical plate, before the case that we had, in all of this case, it was for the scenario that the temperature of the plate is constant. TS, the whole from here to here is TS. The temperature is constant. The temperature is constant. The temperature is constant, okay? But in the case that other boundary condition, as I mentioned, like a constant heat flux, the temperature is not constant, but if we provide a uniform energy to the plate. Therefore, in this case, we define a temperature of the plate, and the temperature of the plate is the mid temperature, okay? For isothermal plate in table can be also used for plates subjected to uniform heat flux, okay? It means you're heating that plate with a heater. The temperature is not constant, but you're providing a uniform velocity throughout the length. Probably the temperature from the bottom will be different from the temperature at the top. Therefore, we define the temperature Ts, the midpoint temperature. And we can use the same thing as before, okay? Midpoint temperature is used as the temperature of the plate. Okay, therefore we use this one to calculate all the physical property and Grashof number and do that. Any question? Okay. Now we can have an inclined surface again here, the hot plate. Therefore, as we can move up because of the temperature changing, we mentioned the profile will be different. In a hot plate, in a cooler environment for lower surface of the plate, the convective current is weaker and the rate of heat transfer is lower than upper plate, okay? So you can see in this case will be different from the vertical plate, okay? That's it. On the upper surface of the hot plate, the thickness of the boundary layer and thus the resistance to heat transfer decreases and the rate of heat transfer increases relative to the vertical plate. Okay. Therefore, that in this case that you can see, we have a variation of the movement of the air and also the recirculation here. Look at here, is I have a hot plate that move here, and because of the temperature difference between the plate that you have here and the air here, the buoyancy here is stronger than here, okay? Therefore, that's what we're trying to mention. If you have horizontal plate, look at the horizontal plate that you have, the hot plate that you have right here, okay? Because if the temperature here is hotter than air, natural convection takes place back here, okay? Because the air gets lighter and move up here, okay? That's happening exactly up going through. Therefore, here, for a hot surface in a cooler environment, try to imagine, just don't look at the word here, just try to say, hot surface, the temperature of the surface is hot, and the temperature of the room is less. Therefore, that causes the air right here can get warmer and move up, okay? If the hot surface facing upward, if this surface fully dries and is create an environment, because here all the air come here, get hot, and they would like to move up, and there is no restriction, and that goes keep up. But look at here, please. Try to understand again the physics set and try and also use imagination. But if the hot place is facing down like this here, the hot plate blocking the air movement, because all the hot air is right here. They're not coming down. Look at here. This is the air infinite. The temperature of the room is cold and come up there, get hot, and there's no place for them to go. And therefore, we have to be able to understand the difference between here. Here, the convective heat transfer is helping the air go up because they get cold and go up. But here, all the hot air is up there here, and there is no place for them to go, okay? The opposite true for a cold plate in a warm environment. Therefore, trying to understand here, okay, what is the difference physically, what is the difference here? Again, remember when we're talking about natural convection, we're talking about the density. And we know the simplest one is ideal gas law. In the case of ideal gas law, the temperature increases, the density decreases. And therefore here we're trying to characterize the case of what is the characteristic length, okay? Okay. Now, the same thing happened again for the next geometry. We're talking cylindrical coordinate. Again, the temperature is hot. The air cold air closer to the cylinder, and as it gets up here, get warmer, 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 and therefore here the thickness of the bonded layer is higher, thicker, and leave up down here. Here, the down here, they are approaching. Therefore, this is the bonded layer to scale. Again, please put the writing, put it here. Just as you look at this picture, try to relate to the physical phenomenon. For a hot horizontal cylinder, start to develop at the bottom. Here is a pipe. Here is the room air. This is hot. The air get close to here, become warmer. Therefore, here is the bonded layer thin. As move along the pipe, the bonded layer becomes thicker, thicker, and goes all the way, and then leaves here. The bonded layer over hot horizontal plate is started at the bottom here. Increase the thickness, as you can see, as it gets here, the thickness of the bonded layer increases, and then become plume, and then go up. Therefore,
Sir?
Yes, sir.
Does it stick to the hot cylinder because of viscosity?
Again, the viscosity, again, look at here. We're talking about between the two forces, the competition between two forces. The surface velocity, the velocity of the surface of the pipe cylinder is 0.
Yeah.
But as we go up here, there is no temperature difference anymore. Therefore, there is no movement here.
Okay.
Therefore, here, the velocity in this range becomes like here. Okay, the velocity here becomes 0. The velocity here is the same thing we said.
Yeah, just like the wall we saw before.
But here, as move up here, the contact time between the air and the cylinder is increased. As the pipe becomes bigger, there's more, the thickness increases, okay?
Okay.
If this cylinder is cold, becomes the opposite. Cold air comes here and goes down here. Therefore, the local Nusselt number is highest at the bottom and the lowest at the top of the cylinder when the bonded layer remain laminar, okay? They're talking about local, my friend, not the average, local Nusselt number. The opposite true in the case of horizontal cylinder, okay? Therefore, again, The idea here is, at this moment, this is introductory book by this courses. They gave you some equation. The idea here, we have to be able to relate to the physical phenomena that's taking place. Again, we have to understand what are the parameters influencing this movement. The parameter influencing movement here is the buoyancy and viscosity, okay? And that's represented by a number called Grashof number. The same thing again, we are dealing with the fin. Again, the same process that takes place for the fin. That let me go further, then we come back later on to this one. Okay, I'll come back later on this one because at this moment I will look at this part. Now we go back again. So far we dealt with only one plate because one vertical plate, the temperature of the plate was hot or cold. If I come back to the same physical phenomenon, take place between two plates, and that's exactly what happened between the two glass of window. One of them here, one of them here, and we have an air gap in between. Look at the winter, the surface here outside is cold. It is a room temperature, the surface inside is hot. Again, look at here, we are talking about a small gap between these two. The air close to this window, right, this glass here, is hot. Look at here, is moving up because the temperature of the plate here is higher than temperature air here. Therefore, this becomes hotter and go up. Then let's look at this surface. This temperature, this side of the surface is cold compared to the air in here. Therefore, the air going down, become colder and go down. As this can go up here, therefore you have this circulation all the time. So far in building science, we look at there is conduction, but in reality, we have also convection. We have conduction and we have also convection, okay? Therefore we have two physical phenomena taking place simultaneously. Therefore we are talking now here is natural convection and enclosure, okay? Because this air is influenced by this surface, this air is influenced by this surface. Therefore, we have this recirculation come. Still, we have to go back on the same number. We have to calculate the Rayleigh number. When it comes to the Rayleigh number, we have to define what is the characteristic length. The characteristic length is important. In this case, mentioned the characteristic length is the distance between the hot and plate. It's not the length of the plate. It is not this one. The characteristic length, this one. The distance between these two. Okay? Therefore, now, temperature of the surface is one is T1, and the other temperature is T2. Therefore, this temperature difference between these two surfaces are dominating this physical phenomenon. Therefore, keep in mind when you're trying to look at enclosure, again, my friend, again, this is something some student made mistake. We are dealing with this air movement between these two plates. Hot plate, cold plate, and the space between them is L, and that's the characteristic length. Please read one again. What I said here is the enclosure of frequently controlled in practice, okay? In a vertical enclosure, this is again, could be vertical, could be horizontal. In horizontal, we're dealing with a solar collector. Solar collector is always horizontal. We are not putting vertical, putting horizontal. Okay? Hotter surface, enclosed vertical, the fluid adjusts to the hotter surface, rise, and adjust to the colder place goes down. Therefore, this is rotation continuously happening. Okay? Continuously taking place. Okay? And again, is natural convection because there is no fan inside. This is sealed. Therefore, we have to calculate Rayleigh number to find out if it's laminar or turbulent. But to keep in mind when we are using this equation, the characteristic length is not the length of the window, but the gap between the window. And then when you're using this equation, you have to look at the temperature of one plate hot, one plate cold. Keep in mind, this is here, there's no temperature of the air. This is the surface temperature. Again, the same thing happened when we have horizontal. Okay, horizontal, look at here, you have hot plate up, cold plate down. What will happen in this scenario? Imagine you have a hot plate up there and cold plate down here. All the cold plate, hot plate. All the hot air is going to stay here. All the cold air is going to stay here. There's no movement. There is no motion. This is only pure conduction. Okay? Because all the cold air is sitting down, all the hot air is sitting up there. There is no movement of the air. Okay? Therefore, don't look at here. Okay? But look at the opposite scenario when you have a hot plate down and cold plate up. The hot air go up, get cold, and comes down. Therefore, you have here, this is happening. That's, we call them is honeycomb. They're trying to improve this losses. They put this top of that, they break down this big one to a small one. Okay. Therefore, look at here, this scenario. Please understand the physics again. If you have a cold plate and if you have a hot ceiling that heated up there, you have no convection. The only thing heat transfer is by radiation. And you can see it sometimes in some warehouses. In some warehouses, when the worker they place, they put them in sort of a heating element on the top of their head. They are heated only by radiation, but there is no convection because hot air is up there, the cold air down here. The cold air does not have energy to go up. Therefore, it's sitting down there, and the cold air, hot air sitting up there. Okay, therefore in this case, we have only pure conduction, but here in this case, we have convection. Okay, natural convection occurred is this one, Rayleigh number turbulent for this one, okay? And again, the physical property, again, we don't have the air temperature. We are dealing with two cases, T1 and T2. All of them we calculate based on that. Okay, any question here? Any question? Okay, I have 4 minutes left. As I mentioned to some of you at the beginning, and now the podium is open for complaint. What difficulty that you had during the exam? Because I'm trying to learn from your problem that I can communicate it with university. I noticed some of you had difficulty to link, and some of you had a difficulty to upload your solution. What else?
Sir, I'm not sure if it's only me. The exam finished earlier than the time is supposed to close. The screen just shut down before. I
believe it was mentioned. I do not know again, but I just read it quickly because I haven't gone on the equally yet. But it mentioned they gave you 145 minutes or 2 hours. I do not know how much time they give it to you.
On the screen, it shows still 7 minutes, but suddenly it's just closed. Maybe the 7 minutes is left for us to upload the photo. I was not sure about that. But this time is fine. I finished before the window closed. I'm just wondering what's the time frame to upload photo and the time frame.
Again, this is I'm as naive as you are because I never worked with the system. I'm trying to learn it myself. What else? Because I know you have some of us have the problem with logging time, some of them with uploading your.
What happened to me is I was asking the guy if there's extra time for uploading. He told me you have to send him a private chat in the Zoom. Once I left the green window and go to the private chat to chat with him, I was kicked off the call. So,
you see?
Yeah, the system of communication with the invigilator was like very deficient because like either you were disturbing everyone because there's like problems and like they had no way to manage it, and as soon as you were clicking on something it was kicking you out, so you have like no support. And like usually we don't speak during an exam, but then people had no choice.
Yeah, okay. What else? As I mentioned, the only thing I can pass is all of your difficulty that at least they can take in consideration for the final.
I think that the hardest thing was the invigilators calling on people during the exam. It was very hard to concentrate with them constantly calling names and calling people. Like it was very distracting. I don't know for anyone else, but
why they call them?
I guess because they were maybe flagged for cheating, or I don't know, but they would say like, excuse me, and then the name, but then the person wouldn't react, so they'd repetitively call on them, and we could hear all of that. So that was extremely distracting during the exam to be able to concentrate.
Yeah, I agree also. It was either the invigilators talking or students talking because they had problem, but it was constant talking throughout, or like very often there were people talking and it was very hard to concentrate. I found that as well.
Like a good 35 minutes at least during the exam was like technical problem and talking because people had no choice, but invigilator were talking a lot. And like I even asked them to stop, but they didn't.
Also,
because they cannot the microphone on, because they would like to make sure from your side that they can hear. But yeah, I know. Okay, I understand the problem. Okay, yes, I'm sorry.
Sorry, I was just going to say I'm not sure if it was the case for the other group as well, but either the explanations went a little too long or the sign-in took too long, and they were actually still talking. Like we got a late start to the exam, basically. I think we lost about 10 minutes.
Yeah, it was the same for me also.
Yeah, that's true.
yeah, same here.
Same.
Okay.
I'm sure many of the students could have used those extra minutes as well to complete their work and not struggle with the time lapse that was already limited. So I think that was deficient for most of the students as well that could have used those couple minutes that were lost on the TA's side.
Mm.
Also, sir, I had good internet connection and I had a good webcam and everything, but my computer froze in the middle of the exam, and they said that I should restart because I called them, and then they said that I would get extra time, but I wasn't given any extra time, so I wasn't able to finish, but I was able to upload my exam, so I'm not sure about that.
Anyway, what I said, I took at least I know 5 issues. I will try to communicate with them and let them know, because I know this difficulty. Again, they have a certain constraint and you have a certain constraint. We're trying to sort of optimize at least to be less stress on you. Again, I believe you know me, I'm from building science, right? Remember me? I mentioned this as an exercise, trying to work hard and trying to understand the subject. And if you do extremely well in the final, we try to help you to get a better mark. But please, because again, this is between me and you, trying to behave well during the quizzes.
Sure. By the way,
the quizzes, let me be a little bit explicit. 10 people cannot make the same mistake.
Sir, by the way, can we have the solution for chapter 7 and 8?
I can give you the solution chapter 7 and 8, but please behave well during the quiz, because it seems some of you, not all of you, some of you are not behaving well, okay? Because it's not possible to 5 or 10 of you make the same mistake at the same time, okay? Trying to focus, trying to understand, that's okay to make mistake in quiz, because that way you will learn, but you don't have the chance in the final exam. You have to focus to understanding the fundamental, the physics of the problem, and the focus has to be in the final exam. Please study, and we are here to help you. I will send you the solution to assignment number 7 and 8 shortly. Study hard, is only 3 weeks or left, and let's get a good outcome of this course. All the best.
Sorry, I have 2 questions.
Okay. Let's make the first one.
Yes. First one is regarding the marking. Do you give points for
I don't give anything to anybody. I don't give anything to anybody. I would like to make sure that you understand. Okay.
Not give freely, but if we deserve them.
Of course, whenever you deserve, you get full mark.
Well, if the final answer isn't right, but the process is
yeah,
right.
that's again, you know that I have to mark 70 something papers. Okay, therefore I don't do it randomly. I mark if this done this part to get this portion of the mark. If you get this part to get this portion of the mark. If you get this one portion of, because this is create less stress on me, and it's become more uniform, fair to everybody. I don't mark just 50% randomly. No, I go line by line to make sure the focus here. I want to make sure that you really understand it. Okay, and that's with as you go to step by step, you get a portion of the mark.
Okay, but what if all the steps are right, but only a calculation mistake?
Again, we have to see which part of the calculation is mistake. Okay, and when again, this is a hypothetical question that I mentioned. If it's the first step hypothetical mistake or the last step is mistake. Again, that's depend.
Sorry, sir.
Yes, sir.
Is the final going to be after chapter 6? Do you have an idea?
The final, chapter 6?
Well, the midterm was until chapter 6, no?
Yeah, the midterm, but the final is going to be until end of chapter 13, sir.
Okay, everything. Okay.
From the first until the last.
Perfect. Thank you.
Sure. Okay, all the best.
Sir?
Yes, sir.
There was my second question.
Oh, yes, your second question.
Yes. Well, maybe it was me who didn't understand it, but if there's a mistake in the question, what do we do then?
Was there a mistake in the question?
Well, I think it was in the units of the...
Convective heat transfer.
Yes, there was some...
The potato.
It was
something weird, yeah.
It was
it was instead of being for the convective heat transfer, instead of being over meter cube, it was on meter square. It was on meter cube.
And like Celsius instead of Kelvin, and like.
No, that's it.
But that doesn't matter.
That doesn't matter. Good. That doesn't matter. But again, everybody can make mistake, including your professor. But you know the conductivity units, therefore you know that it's not based unit of volume, it's based unit of area.
Okay, so
that should not affect your answer to the question.
So for the midterm, like according to, well, like as you said, this should not affect, but like all the rest, like what are the action that will be taken toward what happened or what is investigated toward what happened?
Moment, again, the question at this moment, my answer, my official answer to you here, I will follow considering there is nothing happened, okay? I marked the paper to give you the feedback to you to see what is your understanding of the subject. To be fair to you, in order to encourage you to work hard and study and work hard and hard and hard, I give you the chance to get A+ if you do well in the final exam. That's all I can do. Because it's very difficult to go case by case because I do not know what happened. Again, we are trying to work with the university and inform them. You gave me some list of problems. I'm going to discuss with the university to make sure this will not happen in the final. But the focus, your focus has to be trying to understand. If you have any question, the TR, I believe both of them are excellent. They are there to help you, and I'm here to help you. Try to work in the final. And this exam, you know better than me how much that you really know the subject and how much you do not know. It's not a question of the mark. You, at this moment, you have the time to test your ability. And we are here to help you. And as I mentioned, I'm with you. I'm trying to make sure that you get an excellent mark, but you have to work very good, that we ignore the midterm and to give you the full mark for the exam.
Sounds fair, sir.
I always am fair, sir. Thank you for approving it.
Thank you, sir.
All the best. Take care of yourself, gentlemen.
Have
Bye
a great day.
You too, madam. Bye-bye.
Have a good evening.
Have a good evening.
Sir, actually, I do have some feedbacks.
Yes.
Well, for the exam, what happens is I work on the laptop, so the camera is built on the screen. And when the exam begins, the invigilator didn't say that my angle is not appropriate. And during the exam, he sent me the private message and I was working on the exam. My screen was locked, so I couldn't see the message. And he was saying that he wants to see my hands, which I couldn't do because once I pull the screen down, I cannot see the question. So she just asked me.
And again, this is again, my friend, look at here. There is a lot of constraint with you, your side, and their side. And the question, trying to make sure this will not happen in the final, okay? Because the final is very serious, okay? Therefore, make sure that, as university mentioned, they are providing you with the camera, they were going to provide the laptop and so on, that make sure that everything is done fairly, okay? Because remember, there are 70 students in this class. And if you summarize, you will end up with 70 times 70 type of excuses. And the system has a certain limitation. University mentioned that they can provide you with camera, they can provide you with laptop, that this will not happen again, okay? Therefore, you know the system, you know the limitation, prepare yourself for the final. Because this is, again, there is a limit that they cannot pass that limit. You cannot accept every type of issue. Therefore, you have to take some steps in order to reduce the number of the problems.
Sir, I think what he was saying, because I experienced this as well, it was the invigilators weren't on the same page regarding where the camera should be pointing. Some of them would ask us to point it at our face, the other half would ask to point it at the paper. So they among themselves weren't clear on where the camera should be pointed. So I think that was the only thing.
Again, for camera, again, this is as I mentioned, those are people who are sitting there that are not experts. They have been told to sit down and try to do that. I understand your point. We're trying also to address this issue, that they be all the invigilator to be trained properly, that they can be sort of uniform.
Yeah, just so we get the same instructions from
Yes,
everyone.
Yeah, I understand. Again, all the best. Yes, sir.
Sorry, keep cutting you. One thing I want to kind of complain is the TA. He held an office hour before the midterm. First of all, I have to say he's very nice and very helpful, but actually we did 3 questions on that office hour and 2 of them took so long. And well, obviously it's because he's not super very good on his explanation. I just hope he can improve a little bit so he can be helpful, because even for the last question, I was kind of helping him out to help another student. So yeah.
You're talking about he or she?
He is Connor.
Okay, Connor. Okay,
I would say that, okay.
I will discuss with him. I will mention in general term, he has to be well prepared when we go to the tutorial. Thank you again. I appreciate that you're telling me right now, because at least he has time to improve himself.
Okay, thanks.
Take care. All the best.